otherwise too much. The thing I want to talk about now is the so-called completeness of the basis. Okay. Completeness, it means what? It means your basis vector should be able to represent every vector in the space. Remember what is a vector? How do you represent vector? It represents a linear combination of the basis vector, right? If I have a 2D plane, then the x and y can represent the 2D plane very well. The set of x hat, y hat is the basis for a 2D space, 2D real space. Okay? What if I have a vector sticking out? Can it be represented by x hat, y hat? No, right? Then it's not complete if you only say that x and y. The complete basis needs to be, what is the complete basis to represent a 3D real space? Exactly, x, y, z for 3D real space. We know this very well. Okay, right? In general, now if I put a set, I just call it I, it means I have a set of basis vector. If it is complete, right, with, of course, I equal to 0 all the way to n minus 1. What dimension is this? N, right? Then any vector can be represented as a combination, I equal linear combination of this basis vector, which you know already, alpha I times I, right? Alpha I times I. You know this very well already. Okay? That is good, right? There's nothing special. But then from here, we're going to derive a very important property of completeness, which will be very useful in the later derivation. What if now I apply, for any vector, I apply the basis vector to it to form the, what is this? What does this mean? Again, what does it mean? Or V on J, right? We find the inner product of J, and J is a basis vector on V, right? So what does it look like? J operates on summation of I equal to 0, n minus 1, alpha I. Okay? Looks very weird, but do not forget, this is just addition. And the linear, we already showed that it obeyed the distribution law, right? Earlier in the bracket operation. So this is equal to I equal to 0 to n minus 1, alpha I, j I. Do you agree? Because basically this is just a number times first vector, another number times another vector plus another number times the third vector. Do an inner product with j, like this. This is just like j operates on alpha 0, 0 plus alpha 1, 1, all the way to alpha n minus 1, n minus 1, right? And this is just equal to alpha 0, j 0 plus alpha 1, j 1 plus all the way to alpha n minus 1, j n minus 1. Make sense? That is what it is saying here. What is j dot I? What is the inner product between j and I? What is j and I? What is j and I? What are they? What we just said. What is this? The basis vector. So what's the property of the basis vector again? Say again? They are orthonormal to each other, right? So this becomes what? Yes. They are orthonormal to each other in this class, in quantum computing, delta ij. And it is only 1 if I equal to j, right? So this is equal to alpha j. Correct? Because all other I are 0. And you can see it from here already. J dot 0 is 0. J dot 1 is 0 until J dot j is 1. And then J dot n minus 1 is 0. You only have alpha j left. Make sense? So alpha j equal to this one, okay? Then now I'm going to substitute 1 into 2. You have V equals to summation I equal to 0 n minus 1. Alpha j is just a number, right? So alpha j equal to j dot j inner product V. Then alpha I is just equal to I inner product V. This is just alpha I. Okay? Yeah. Because they are the basis vector, they need to be orthonormal in this class. Now, we can do what? What is I times V? Is a number, vector, or matrix? I dot V is what? Scalar, right? If a scalar, I can move it to the back, right? There's no problem of doing that. It's a number, I can move it around. Correct? And then I have this associative law. I can also do this first. And just now when we say what is the outer product of a matrix, what is that? It's a matrix. So you basically see a matrix applied to a vector, do the summation, is a vector, which makes sense. So this is telling me that, but V does not depend on I, right? This one is just equal to summation I 0 n to n minus 1 I, the whole thing applied to V. V equal to something applied to itself, no matter what V. Okay? Any V. Then this guy, what is this guy? What? It means that it does not change me, no matter what it has to be identity. Okay? So if your basis is complete, then finally, we have this very important equation. Summation I equal to 0, n minus 1, I is just identity, just an identity. It means the outer product of all the basis states, and you add them together, the sum of the outer product of a basis state is an identity matrix. And when you have identity, you can insert to anywhere in your equation, right? Like multiplication, you can multiply 1 at any place. It doesn't change anything. Then you can simplify many things. You will see that. Now maybe I will stop here today. Like an example. Yeah, I swapped that one. Let's just go back to example of the eigenvector of C. Sigma C, right? We just say that it is 0 equal to 1, 0, 1 equal to 0, 1. I do want you to really understand this, what I'm saying. I say 0 and 1 here in the cat is meaningless. It's just a name. You can say first vector, second vector, happy, unhappy. Okay? Yes, no. But then this is math, 1, 0 and 0, 1, because they are really column representation. But the first one is talking about you have one part of the first vector. Second one is a 0 part of the second vector. And since we're using the eigenvector as the basis, then of course you have one part of the first vector for your first vector, right? Your second vector has one part of the second vector as the first vector. Okay. Then let's take a look if this is true. This time, okay, let me write this down. N minus 1. Can you tell me, first of all, right, what is n in this case? What's the, 2? What's the meaning of n? How many bases, which means the dimension of the space, right? So this is 2 dimension. N equal to 2. So what I care is summation I equal to 0, 2 minus 1, I. Okay. Then I spell out the summation. I equal to 0 means 0, 0. And then the last one is 1, 1. Is this okay? Now, what do you do? How do you do the outer product of 0, 0? Again, 0, I just write it down as 0, 1, 0. Right? Bra is 1, 0. For 1, the bra is, the cat is 0, 1. The bra is 0, 1. Now, can you do the matrix multiplication? Row times column. Row only have 1 element. The column only have 1. The first one is 1 times 1. 1 times 0. 0 times 1. 0 times 0. Right? The second one is what? 0 times 0. 0 times 1. 1 times 0. 1 times 1. Which is equal to 1, 0, 0, 0. Plus 0, 0, 0, 1, that is equal to 1, 0, 0, 1, which is the identity matrix in the 2-dimensional space. Yeah, someone say to the power n. So I spent so much time, I don't think other classes will do this, right? Because I know that I also learned quantum computing myself. What are the most difficult concepts? If you can understand this, then the rest will be easy. That's why I keep repeating this naive and trivial step. You need to really understand every tiny bit. Okay? How about the eigenvector of x? Of sigma x. Does it span the space? Now we call it plus, call it minus. We are representing in the sigma c eigenvector basis. So if you forgot, it is 1 square root 1, 1. You did this in your assignment already. Minus is 1 square root of 1 negative 1. Yes. Okay. Right, so let's just check, repeat. What is the n in this case? What's n? 2, because it is still 2-dimensional. We have 2 bases. Okay, so summation I equals 0 to 2 minus 1. I still call it I because this doesn't matter. It's just a number. I try to index it, right? If I spell it out, basically I'm talking about plus minus. It's just a name. I call it plus minus. If you really want to call it 0 and 1, no problem, as long as you don't get confused with the eigenvector of sigma c. Okay, it's just a name. But what really matters is when you substitute the column vector. The plus, it becomes 1 square root 2, 1, 1. This becomes 1 square root 2 of 1, 1, but row. Minus is 1 square root 2 of 1 negative 1, 1 square root 2 of 1 negative 1. Okay, is this clear? The rest is just math. Okay, so let me move a little bit faster. this becomes 1/2 because I have 2 square root 2, 1, 1, 1, 1, right? 1/2, 1 negative, 1 negative, 1, 1, right? Because 1 times 1, 1 times negative 1, negative 1 times 1, negative 1 times negative 1, right? So if you really do this, it becomes 1/2. 1 plus 1 equal to 2. Actually, quantum computing is very easy. We always just deal with 0 and 1 and 1 plus 1, which is equal to 1, 0, 1. Again, identity measure. Yeah.
So how
okay. This is in the sigma C basis, right? This is not sigma X. Is that what you're asking?
Yeah.
Why, if I put in the sigma X basis, then it becomes this, right? You are saying that why they are different in different bases, right?
Yeah. So yeah, it's the same sigma X, different vector. So you have to present to the sigma basis, that would be and that would be the vector.
Sigma X basis vector, eigenvector, if you represent in the sigma C basis, it is in this form because it is equal to 0 plus 1 square root. Right. It's just like what we discussed before, which is wrong concept, but it illustrates pretty well. This is like the sigma C basis. And this is like the sigma X basis. So for a basis vector here, for example, plus, this is the plus, this is plus, 1 plus. If you represent in the sigma C basis, you have one component due to 0 and one component due to 1. And that's why you will write it as 1, 1. If I write it as 1, 0, then it means I only have one component due to 0. Right? It makes sense?
Yeah, it makes sense.
Okay.
So
Good question. Yeah.
Sigma X and sigma X basis is just 1, 2, and 3.
Yes. Yeah. Because you are just asking, how do you represent my eigenvector in the basis formed by my eigenvector? Right? So my first eigenvector equals to my first eigenvector, just like this. Okay. Good question, right? We need to make this very clear because if you want to continue to work on quantum computing, you will see all the algorithms keep changing the basis because they make it easier to understand, easier to manipulate if you change the basis. The physics is still the same. But if you don't do this well, you will get lost. Right? So this is a very good discussion. Any other questions? Okay, so let me take the attendance quickly. Right.